Hello and welcome to our next lesson on exponential functions. So by now you should be familiar with exponents and have some practice using exponent laws to simplify and evaluate expressions. So today we are now defining what exponential functions are, as well as looking at how their graph looks like and comparing it to some of the functions that we do already know. So with exponential functions, you will have a function that looks like y is equal to a to the power of x. So we have that base and its exponent where x is our variable that's changing and a is the base that is constant. And we are looking at a greater than 0 and also a is not equal to 1. And the reason a is not equal to 1 is 1 to the power of any exponent is just 1. So when you have y is equal to 1x, then any x value will just give me 1. So this is just y is equal to 1, which is a linear function. So it is a horizontal line and it is not an exponential function. So a has to be greater than 0 and not equal to 1. So first consider these six scatter plots below, and I want you to think which one represents an exponential function. And specifically consider which of them look like functions you have seen already, and we are going to eliminate those and see what we are left with. So right away, I hope this one reminds you of our quadratic function. So y is equal to x squared, or it could even be y is equal to x to the power of 4. So that one is not going to be an exponential function. This one does have potential to be an exponential function. We can see that it is rapidly growing as x is growing. So this one actually could be an exponential function. Now this one, you may have seen it before. This is our cubic function, which has this shape. And the reason for it is, as we saw previously, when you have negative values for the base, then you do end up with negative values over here. So, for example, when x is 2 versus when x is negative 2, we would have y is equal to 8 versus here it would be negative 8. And that's why we see that for the negative values, we actually do have negative outputs because of the odd number for the exponent. Now, this one, it's pretty much a line, right? This is our linear function. This could be something like y is equal to x. And this one, we are going to see this later on, but this is a repeating function. So this one is actually also not an exponential. Now, this one as well, we see that we are rapidly decreasing in this case. So this one could also be an exponential function. So we only have these two. So just to summarize that, scatter plots that grow rapidly or shrink rapidly in a non-linear pattern can be modeled using exponential functions. So here we can see that this is exponentially increasing and this is exponentially shrinking, and they are growing in a non-linear way or a non-linear pattern. So these have potential to be the graphs of exponential functions. Now, here as well, the range of an exponential function with a positive base always has a lower limit. So what that means is, consider 2 to the power of x, right? So any x value that I put here, so consider first 2 to the power of 0 is 1. And then we know that 2 to the power, when x is greater than 0, then 2 to the power of x is also going to be greater than 1 because it's growing. However, when x is less than 0, so for example, when we had 2 to the power of negative 1, remember this is just 1 over 2. So really what this means is, or if I keep going 2 to the power of negative 2, this one would be 1 to the power of 4. So as I keep going towards negative infinity with my x values, then I will actually never reach a negative output. My outputs are always going to be positive because 2 or my base is positive itself, which is what this is telling us. There is always a lower limit, which means that your output y is always greater than 0. you will have infinitely small decimal values, but they will never be zero. And that's kind of what we can see here. For example, this would be the y-axis. For example, let's say this is y is equal to 2 to the power of x. And we can see that this is growing as x is growing, but as x is decreasing, then this will just keep going towards the y is equal to 0, or sorry, the y-axis line, but it will never actually pass it and go into the negative. So we have a lower limit there. And we just saw the two cases. So when the output is increasing or decreasing, and these are the two names for it. So we can have an exponential growth or an exponential decay. So exponential growth are when situations are increasing. So we have the function that's increasing, such as this green one here, and this one will be our exponential decay because it is rapidly shrinking or decreasing. So um, exactly as mentioned here, the output of the function grows rapidly and in a predictable way. And this is exponential growth. However, when it is decreasing in a predictable way, then we say that it is an exponential decay. And you will see these two terms used a lot in our application problems. So please make sure you remember them and you know which one is which. So now we're going to compare exponential functions to two functions that we're very familiar with, which is our linear functions, our quad or power function. So in this case, we have a cubic function, but quadratics would work as well. So pretty much our polynomial functions, and then the exponential function itself. So I'm going to give you a moment first, try to fill in these table of values, and then we are going to analyze them. So your completed table of values should look like these. And the question for you here, what type of functions are these? And I already mentioned this earlier, but this one would be our linear function. This is a cubic function, and this one is now our exponential. And for this one, I can also write polynomial as well. And now we're asked to compare the first and second differences. So remember, first differences are when you subtract the outputs and find the differences there. So for example, in this case, we would have -6 minus -9, which would give us 3. Maybe I'll move this over a little bit. And similarly here, -3 minus -6 will give you 3. And 0 minus -3 will give you 3, and so on and so forth. And second differences will now be if you take the difference of these first differences. So I'll give you a moment to try that on your own, and then I'll share the final results with you. So I've set it up like this, but let me go over it and explain it a little bit. So if you continue this with the linear function, as we just saw, and we already saw here, we had 3, 3, 3, and if you continue on, all of these will be 3. So the first difference will all be 3. And so based on that, if you take the difference of those, you will actually end up with a second difference of 0, and then so on. And if you keep going and taking the differences after that, they will all be 0. Now, with the cubic function, so if you take the first difference, that's the first difference shown there, you see that they're not constant. If you take the second difference as well, they're also not constant, which is this one might be a little bit new for you. If you had done this previously with quadratic functions, we would always expect that the second difference to be the same. But consider quadratic functions are to the power of 2, whereas here a cubic is to the power of 3. So here, if you actually evaluate the second difference, you would have seen that they're not equal as well. And so you would have been a little bit confused, but here's where you actually have to take the third difference, which is the difference of those second differences, and then you would have got that to be constant, and it would have been 6. So one new piece of information here would be that for polynomial functions, their the difference of the outputs will be the same when uh, based on the power. So with quadratic, again, remember it's exponent of 2, so the second differences were the same. But in this case, because it's a cubic root, so it's a power of 3, the cubic or the third differences are the same. However, with exponentials, you will actually see that neither the first, second, or third difference will be the same, and they actually don't have a constant difference at any point because they are growing exponentially. So there is a pattern, but it is not one we can find with first and second differences. So now we are seeing the graph of those three functions here. So the linear we're used to is just a linear line. This is our cubic root function, which again, remember, because the negative bases will have a negative output, that's why we go into the negatives here, and this one will just stay positive. They do have the same shape, but now just going into the negative outputs. And finally, our exponential function here, we can see that it is rapidly growing, and this is that lower limit that we were talking about. So here we can see that with x being -3, our output is 1 to the power, 1 over 27. And as we keep going towards the negative infinity, our output will be shrinking exponentially, and it is getting closer and closer to 0, but it will never actually reach 0 because 3 to the power of x is not equal to 0 for any x. And as such, it will never actually pass the y-axis the x-axis, and so it will also never have a negative output as well. And that's our definition here in asymptote. So an asymptote is a line that a curve approaches but never reaches on some part of its domain. And we have already also seen this with quadratic functions, so this should be just a review, but they could be vertical asymptotes, horizontal asymptotes, or oblique asymptotes, which are diagonal lines. And in this case, we actually have an horizontal asymptote, which is our x-axis, and we see that this curve will actually never reach the x-axis, making it an asymptote. So now we're just going to be analyzing the domain, range, intercepts, and the equation of any asymptotes for each of these functions. So with our linear function, we know that the domain is just all real numbers. So x can be any value. And similarly, the range can also be any value as well. We don't have any restrictions on the domain and the range. In this example here, the intercept, so the x-intercept and actually the y-intercept are both the same, and they occur at 0, 0. Because when x is 0, the output 3x will also be equal to 0, and that's what we see right over there. And there are no asymptotes. NA, you can write none. And we can see that this line is actually not approaching any vertical or horizontal or oblique line and never reaching it. It's just a linear line on its own. Now, with x to the power of 3, so the domain, of course, we can have any x value, and we can see that the range, we can have any value as well. So similarly, we have x in the set of real numbers, and also y in the set of real numbers. And our intercept here, again, is also the x-intercept and the y-intercept are both 0, 0. And we can see that here when x is 0, then we have 0 to the power of 3, which is 0. So that's our x and y-intercept there. And again, in this case, we don't have any asymptotes because we're not really approaching any horizontal line or vertical line and not reaching it. So here we also have none, or NA. Now, with 3 to the power of x, so our domain, I can't choose any x value that I want. However, my output or my y value is always restricted because of that lower limit, right? So I can have x in the set of real numbers, However, this is going to restrict my range where y is greater than 0. And it's actually not even equal to 0 because as we just said, we cannot have 3 to the power of x be equal to 0 for any input of x. Now for the intercept here, so of course when x is equal to 0, that is one of our options. So we do have a y-intercept, which is 0, 1, because 3 to the power of 0 is 1. However, as we just said, when y is equal to 0, that means that we are never reaching the x-intercept. So the x-intercept is none, NA or none, because um, the function never intercepts with the x-axis, as we just saw. However, we do have the 0, 1 there as our y-intercept. And so here we do have an asymptote, and it will be y, which is just our x-axis or our horizontal line here, where y is equal to 0, and that's our asymptote there. So we did look at the cubic function because I did want to show you something different, but in general, we are comparing linear, quadratic, and exponential functions because that's what we are familiar with. That's what our functions course is focused on with quadratic. So here we are now seeing the table with quadratic functions and comparing the linear, quadratic, and now exponential functions. So with how the function is represented, we know with linear lines, f of x is just y is equal to mx plus b, where m is our slope. And here m cannot be equal to 0 because if it is, then you just have y is equal to b. And so we could have that example as well. It would just be a horizontal line. But we are, for example, looking at ones that are oblique or diagonals. Now, with the quadratic function, we have ax squared plus bx plus c, and here a is not equal to 0 because if a is 0, then you are only left with bx plus c, which is actually a linear function. So to have it be a quadratic function, you need a non-zero coefficient for the x squared to keep that x squared in our equation. And finally, for exponential functions, we have a times b to the power of x. So this is now a new addition we're seeing. We can have a coefficient times the base to the power of x. And again, a cannot be equal to 0 because if it is, then you just have y is equal to 0, which is our linear line. So it is not an exponential function. And we are looking at positive bases. And again, b is not equal to 1 because then you would just have y is equal to a, which again is a linear line or a linear function. So not these two. Now, first differences we just saw with linear functions, the first difference is constant, which means they are the same. However, for quadratic and exponential functions, they will not be the same. Now, second difference is, remember, quadratics have an exponent of 2, so they will have the constant second difference here. And again, as we saw with the linear functions, the second difference will be 0 because if the first difference is constant and you're just subtracting the same thing from itself, they will be 0. And finally, for exponential functions, the second difference is also not the same. It is not going to be it is not going to have a constant first or second difference. And the general shape of the graph, for linear functions, we have a straight line. For quadratic functions, it will be a parabola. And for exponential functions, we have a line that's growing, a curve that's growing exponentially. And this one is for exponential growth, but exponential decay would be just the opposite way, going down. So keep in mind, these are general shapes, so it is not considering transformations. We will look at transformations of exponential graphs later on because we actually will have cases where you will have x and y intercepts for them, but we'll get into that in our next lessons. So now just looking at exponential functions, and we are looking at the basic form for now, which is just b to the power of x, and we're looking at the growth function and the decay function. And again, we'll get into transformations later on. So with our growth function where the base is greater than 1, so we know it is an increasing function, we know the domain can be all real values, and the range will be greater than 0, so not even including 0. And we have a horizontal asymptote of y is equal to 0. Now with the decay function, it's the same, but just now reflected over the y-axis. So here now we have a decreasing function. The domain is still all real numbers. The range is also still greater than 0. And the horizontal asymptote is the same. Again, keep in mind, it's just a reflection, right? So nothing is really changing except for that increasing is now decreasing. They both have that horizontal asymptote there. They share the same y-intercept. And so pretty much a lot of similarities between these two functions. So now we're going to try practicing to graph an exponential function using the table of value. So take a moment, fill in the table of value, and even maybe plot the points, and I'll show you the final answer. So in case you wanted more support, I did want to go over this example together. So this one, 2 to the power of 0, remember, is 1. And this one, just in case you forget ever, is going to be divided by 2 divided by 2. This is times 2 times 2 times 2. So we have 2, 4, 8. And in this side, we have 1 over 2 and 1 over 4. So here the axis is already has a scale, so we're just going based off of that. I will label my x and y axis there. So here, start by 0, 1 is one of my points. I have 1, 2, 2, 4, 3, 8. And then -1 will be half, about there, and there. Okay, and so now we're just going to connect these. And that is my f of x is equal to 2 to the power of x function right there. And you can see that it is exponentially growing. And if I continued this, I would have also had this one as a point here, which is 2 to the power of 4. So you can continue that, and that would be your graph for the exponential function of 2 to the power of x. And now we're going to try this again for 1 over 2. So if you followed my example for the first one, I highly suggest you try this one now on your own and see what you get. So this is now actually the opposite of the one we just saw. So the 0, 1 point is the same, but now we can see that we are actually multiplying by 2 this way and then dividing by 2 this way. And so as x is growing, our output is actually shrinking here, and that's why we have an exponential decay. So, and in this case, I will actually go more towards the 2 before. I will plot this one as well just to have it. There we go. And this is that same shape, but now reflected over the y-axis. So this is f of x is 1 over 2 to the power of x. And so now, how are these two graphs that we just saw similar and how are they different? So first, similar, they have the same domain and range. They have the same y-intercept, which was 0, 1. They also have the same asymptote. And their difference is 2 to the power of x is growing, or increasing. So it is an increasing function, but it is an exponential growth. Maybe I'll write it this way. So it's an exponential growth and it's increasing, but 1 over 2 to the power of x is an exponential decay, which means it is decreasing. And so their shapes are also different their shape will be different in the sense that this one is growing and this one is decreasing, but it is, again, the same shape, just reflected. Now, just to see an application as well, because you might be wondering, okay, what do I use exponential functions for? So consider a bacteria culture that starts with 100 bacteria and the number of bacteria double every hour. So at time 0, we have 100 bacteria. And so this number is doubling every hour. So after 1 hour, we have 200. After another hour, we have 400. Then we have 800. Then we have 1600. And finally, 3200. So what pattern do you notice? And I hope it's clear to see that these are being multiplied by 2 each time. And so the way you identify exponential functions is when their outputs are actually being multiplied by the same value or divided by the same value. So here I can also work the other way and say this is divided by 2, this is divided by 2. As long as it is constantly the same um, term that's being divided or in this case multiplied, then we have an exponential function, which is different from linear and quadratic because linears, they have the same first difference, quadratics have the same second difference, but exponentials are with multiplication. They're not addition or subtraction, they are multiply or divide. So this one is an exponential function. And actually, it will be of the form 100 and then 2 to the power of x, perhaps t because we're working with time. And you can double check this for yourself. At time 0, this is just 1, so we have 100 bacteria. After 1 hour, we have 1 doubling, which is 200. After 2 hours, we've doubled twice, which means 2 to the power of 2 is 4, and 4 times 100 will give you 400. And if you keep going, after 5 hours, we've had 5 doubling periods, so 2 to the power of 5 will give you 32. 32 times 100 is 3200. And so this will be an exponential relation, and you can determine the number of bacteria at any time using this function. Or, for example, you might be asked if you want a specific number of bacteria, let's say we want 10,000 bacteria, then how much time needs to pass for us to have that population of bacteria. And so that was a wrap of our lesson on exponential functions. So I hope you got a nice introduction, especially with the base function. So without any transformations, and you have some practice problems here. And as always, check Google Classroom for any additional tasks posted for you. And don't hesitate to reach out if you have any questions. And I will see you all in our next lesson.